Okay, so 9.5 is on what's called properties of logarithms. Okay, I think I did send you a little handout that had the different properties of logarithms and how you can rewrite logarithms in different ways. Okay, so that's what we're going to talk about on the first few problems. Again, this is 9.5. Okay, if you have a log that is written as a product like this, this can actually be rewritten as the sum of these two logarithms. So this being rewritten as the sum of logarithms would be log base 9 of the first one, which is 9, plus log base 9 of 81. So that's how you would rewrite that log as the sum of logarithms. Okay. All right, number 2. Okay, same kind of thing. Now remember, this is also just another way to write. This is called the natural log. It's log base e, but it's still a log. Okay, so on this one, I'm going to rewrite this one as the sum. Since that's times right there, I'm going to have ln of d plus ln of f. All right, another property of logarithms is if you have a log and it has an exponent, you can rewrite that as a product and bring that exponent down in front of the logarithm, like number 3. So I've got log base n of y to the 20th. Okay, we're actually going to use this one a lot in 9.6 when we're solving equations. Okay, this log can be rewritten as the product using the 20 to come down right here and be times that logarithm. So we'll have 20 from the exponent coming down, log base n of y. Okay, so that's another property. All right, number 4. ln of the 6th root of 7. All right, on this one, because it's asking me to express it as a product. So it's saying it's the same, it wants to use the same property as I did on the last one. But I don't see the exponent yet. But remember, if you are taking the 6th root of something, that is the same exact thing as raising whatever underneath here, which is that 7 to the 1/6 power. So the ln of the 6th root of 7 is the same thing as saying the ln of 7 to the 1/6 power. Now that I see my exponent, I can bring it down in front. So this can be rewritten as 1/6 times the ln 7. Okay. Number 5. Another property, right? I can rewrite, if it's multiplication, I can rewrite it as the sum of those two logs. So if it's a quotient or division, I'm going to rewrite it as subtraction or the difference. So this one says to express as a difference of logarithms. I've got log base t of p over 9 So you can rewrite the quotient, ones that are division, you can rewrite as the difference of those two logarithms. So you'll have log base t of p minus this time log base t of 9. So the quotient can be rewritten as the difference. Right, number 6, same kind. You have ln of m over n. And it wants me to rewrite it as the difference. So let's see. This one will be ln m minus ln of n. Right? Number 7. We've got log base d of x to the 8th, y to the 8th, z. Okay, so it says to rewrite as the sum or difference. There's not going to be any difference or subtraction, right? Because there's not any fractions. There's not any division showing. This is all going to be rewritten as the sum, right? Because that x, y, and z are multiplied together. So that can be rewritten as the sum of each of those logs. So I have log base d of x to the 8th plus log base d y to the 8th plus log base d of z. Now, after you do that, you don't want to leave your logs having those exponents. Okay, what does that property tell me? These exponents can be rewritten down in front of their logs. So let's see, this one will be 8 log base d of x plus, bring down this 8 log base d of y plus, then just drop this one down, log base d of z. Right, number 8. Log base b of p to the 4th, q to the 6th, over m to the 4th, b to the 8th. So it says to write it as sum and differences. So remember, anything that's in the numerator, that's going to be times, right? So those are going to be your sum. You're adding. Everything below that division bar is the quotient rule. So these are both going to be minus in front of those. Okay, so starting off with the top, I've got log base b. Let's see, the first one is p to the 4th plus log base b. The second one will be q to the 6th. Now, like I said, everything below the fraction bar is going to be subtraction. So minus log base b of m to the 4th minus log base b of b to the 8th. Now, everybody's exponents are coming down. So this one will be 4 log base b of p plus, bring down my 6, log base b of q minus, drop down to 4, log base b of m minus, drop down this 8, log base b of b. Now, this one has one more thing that we haven't seen in this section yet. Anytime the base of your log and what you're taking the log of are the same thing. Because what is that saying? That's saying, what power do I need to raise b to in order for it to be b? Well, if you have b and you want it to stay b, then you're going to raise it to the first power. So this whole thing right here actually just turns into a 1. So you really just have -8 times 1 there, which is just -8. Again, that happens if the base and what you're taking the log of are the same thing. The whole thing cancels out and turns into a 1. So you just have, after this last log right here, you just have -8 at the end. Right, number 9. All right, same kind of thing here. So I'm going to rewrite this as sums and differences. The only one at the top is the 4. So I'm just going to have ln of 4. Everything in the denominator, remember, those get your minuses. And I've got 3 separate things in the denominator. So I'm going to have minus ln of 9 minus ln x to the 9th minus ln of y. And then again, anytime you have an exponent, just bring it down. So I've got ln of 4 minus ln of 9 minus, dropping down my 9, ln of x minus ln of y. Right, number 10, log of the square root of c to the 9th d. All right, again, anytime you see a radical, when you're dealing with logs, you want to change that radical into its equivalent exponent. So taking the square root of something is the same exact thing as raising what's underneath here to the 1/2 power. So if I do that, I'm going to have log, and then c to the 9th d is all being raised to the 1/2 power. Okay, now I'm going to rewrite this as the sum. But before I do that, if each of these are being raised to the 1/2 power, I need to do that exponent rule. If you're being raised to more than one exponent, like that c is, okay, if you're being raised to the 9th and the 1/2 power, you're actually going to multiply those exponents together. So let's see, what is 9 times 1/2 give me? Well, 9 times 1 is 9. 1 times 2 is 2. So the c's exponent, since it has 2 and I multiply them together, is 9/2. The d only has the 1/2 exponent, right? Because it didn't have another exponent here. I mean, it does, but it's a 1. Now let's write this, since the c and d are multiplied together, I can rewrite it as the sum of these logs. So I'll have log of c to the 9/2 plus log of d to the 1/2. And then bring down your exponents. So let's see, when I bring down my exponents, I will have 9/2 log c plus 1/2 log D. Right, last one like this, number 11. Log base B. This one's a doozy. Of the 4th root of m to the 12th, n to the 16th, over b to the 3rd, c to the 3rd. Oops. All right, so just like the last one, since it's a radical, the first thing I'm going to do is change that radical into its equivalent exponent. So everything that's being taken the 4th root of is going to be raised to the 1/4 power. So let's see, I've got log base B. Then everything in here, so m to the 12th, n to the 16th, over b to the 3rd, c to the 3rd is being raised to the 1/4 power. So everybody in here has 2 exponents, right? They've got their own individual exponent, and then they all also have that 1/4. So now, to get rid of that 1/4, I need to go through and multiply everybody's exponent times 1/4. So let's see, that's going to give me log base B. Let's see, I'm going to have m is being raised to the 12 and 1/4. So if I multiply that together, 12 times 1 gives me 12. 1 times 4 gives me 4. And then 12 over 4 reduces to 3. So the m, once I multiply its exponents together, its exponent is just a 3. Now you're going to do the same thing with these other letters. So the n is being raised to the 16 and 1/4. So when I multiply its exponents together, I get 16 over 4, which reduces to 4. So I have n to the 4th. Now in the bottom, I have b. It's being raised to the 3rd power and 1/4 power. So when I multiply its exponents together, across on top I get 3, in the denominator I get 4. That one doesn't reduce. So b is being raised to the 3/4 power. And then c is the same, right? It's being raised to the 3 and 1/4. All right, we're getting closer. So now I'm going to rewrite it as the sums and differences. Okay, the ones in the top are the sums. The ones below the division line have minuses in front of them. So I'm going to have log base B. The first one's m to the 3rd plus log base B n to the 4th. And then minus for the bottom ones, minus log base B of b to the 3/4 minus log base B of c to the 3/4. Now, what do you do with all those exponents? You bring them all down. So let's see, this one comes in front. So 3 log base B of m plus 4 log base B of n. Now, look here. Remember what happens when your base and what you're taking the log of are the same thing? This really is just a 1. So when I bring this minus 3/4 down, It's just going to be minus 3/4 because it's minus 3/4 times this 1. And then the last one, minus, bring down this 3/4 log base B of C. Okay, now we're going to be going the other way. It's going to give us 2 logarithms and ask us to simplify it and write it as a single logarithm. Let's look at number 12. All right, number 12 says express as a single logarithm. We've got log base B of 19 plus log base B of 27. Okay, so what does the sum come from? Remember, now we're just going backwards. We're taking it the other way. What did the sum come from? With the 2 logs being multiplied together in a single logarithm. So if I rewrite this as a single logarithm, it's going to be log base B of 19 times 27. And then if you multiply the 19 and the 27 together, you get log base B of 513. Right, number 13. Again, expressing it as a single logarithm. Right, this one, since it's subtraction, what did the subtraction ones come from? They came from the division logarithms. So if I want to rewrite this as a single logarithm, I'm just going to write the first log over the second log. So it's going to turn into log of 1 million over 10. And then once if you can simplify that, you can simplify it. So log 1 million over 10 turns to, if I divide it, it gives me 100,000. Okay, so that's it's asking for 2 answers here. It wants to know what the log is like this, but then it says, okay, what actually is that logarithm? So you could just type that in your calculator, log 100,000, and it's going to tell you 5. Because remember, if you don't see a base, that means the base of the logarithm is automatically 10, and you'd have to raise 10 to that 5th power in order for it to be 100,000. Okay, I actually did take out 14 and 15 from the homework. So we'll just do 16 and 17, and then we'll move on to 9.6. All right, so it wants us to simplify this expression. So since it's a minus, I'm going to turn it into a division or a quotient problem. So it's going to be a single logarithm. ln in the top, I'll have x squared plus 9x plus 18 over x plus 6. Now, in order to see if this simplifies, I need to actually factor in the top and put it in its factored parentheses, because if one of those factors is that x plus 6, like in the denominator, they'll cancel to simplify. So let's look at what the top would be in its factored form. The first thing I need is this times this to get x squared. So it'll be x times x. The other numbers that multiply to equal 18 at the same time adding to 9. So that would be a positive 6 and a positive 3. And since the denominator is also x plus 6, those x plus 6s actually cancel out. So you are just left with ln of x plus 3. All right, last one in this section. All right, last one. So again, it's subtraction. So I'm going to turn it into a quotient. So I'm going to have log up top. I'll have x squared minus 4x minus 21 over x squared minus 9. Now I need to see if these will simplify. So I'm going to factor the top and the bottom this time. So up top, again, to get x squared, I'll need x and x. Now, be careful here, because now these numbers need to do two things, right? They have to multiply to equal negative 21. At the same time, adding to negative 4. So I'm going to use that 7 and 3 pair, but in order to be negative 4, I'm going to need a negative 7 and a positive 3. So minus 7 plus 3 multiplies to negative 21, while at the same time adding to negative 4. Now, the denominator also factors because it's a difference of two perfect squares. It's still x and x for the x squared. Now, what's the number? The same number, and you multiply it together and get 9, 3 and 3. When you do difference of squares, you always have one of each sign, one positive and one negative. So now I see I have x plus 3 in the top and bottom. So those will cancel. So now I'm just left with log in the top, x minus 7 over x minus 3. Okay. Now 9.6. Is on solving exponential and logarithmic equations. Okay, so we're going to use a lot of these rules that we just saw to help us with solving these equations. Okay, looking at one like number 1, this is an exponential equation, which means the x that you're trying to isolate and solve for is in the exponent. Okay, so if you have 3 to the x equals 243. The first method that you want to do is if you can turn this right side into a 3 to a certain power, in other words, change the base of this to 3, then that's what you're going to want to do. So let's see if we can do that by, let's see, what is 3 to the first power? It's 3. 3 to the second power is 9. I'm trying to see if I can make it 243. 3 to the third power is 27. 3 to the fourth power is 81. So I'm either going to hit 243 or at some point I'm going to pass it. Let's see. 3 to the fifth power actually is 243, which means I can rewrite this side without changing it as 3 to the fifth power, right? Because that is 243. So if I bring this down, if you turn your bases into the same number, then you just solve the equation by saying this exponent is equal to that exponent. So this x would equal 5. Right, number 2. You have 4 to the 4x equals 64. So let's see if I can turn 64 into a base of 4, like I did that last one. Let's see, 4 to the first power is 4. 4 to the second power is 16. 4 to the third power is 64, which means I can rewrite this right side as 4 to the third power. Bring this one down. So just like the last one, if you can turn your bases the same, then your equation is solved by saying that exponent is equal to the other exponent. This one just has one more step, right? To get the x by itself, I need to divide both sides by 4. So x equals 3/4. Right? What if this cannot be done, though? What if you can't make the base of both sides of the equation the same? Like on this one, right? You're not going to be able to rewrite 19 with the base of 2 simply. So because 2 to the first gives me 2. 2 squared is 4. 2 to the third power is 8. 2 to the fourth power is 16. But 2 to the fifth power is 32, which means I can't, 19 is going to be somewhere in between here. Okay, so if that's the case, we're going to use that logarithm rule that we just learned in 9.5 that says if your log has an exponent, you can rewrite it, bringing that exponent down in front. This is the same thing as 5 times log to the x. That's what I'm gonna do to get the x out of the exponent. Okay. Now I can do that because I can do absolutely anything I want to this equation as long as I do it to both sides. Okay. So if I log this side, I just have to log the other side. Now I'm going to use this property because now what can I do? I can bring the x out of the exponent. So now I have x times log of 2 equals log of 19. So now that the x is out of the exponent, I could isolate it, right? So if this is x times log 2, so I just need to divide both sides by that log of 2. So this cancels. There's your X all by itself. And then this is calculator work. So in your calculator, you're just going to type in log of 19 divided by log of 2. So again, there's your log button. Log of 19. Now you're going to need to close that. Divided by log of 2. And then close that. Okay, it's going to give you a long decimal and then ask you to round it to 4 places after the decimal. So let's see, I've got 4.2479. I always want to look at the 5th space, right? That's what tells me whether or not I need to round this up or not. If that's 5 or above, then you would round it up. But since it's not, then you don't need to round it. Right, number 4. To the 6x minus 1 equals 16. So again, the first thing I'm going to check is if I can turn this into a number that has a base of 2. Because if I can, then I don't have to use the log rule. Let's see if I can get to 16 using 2's. Okay, so 2 to the first is 2. 2 to the second is 4. 2 to the third is 8, and 2 to the fourth is 16. Which means I can rewrite this to have the same base as the left side, right? What can I say is 16? Well, it's 2 to the 4th power. So over here, I have 2 to the 6x minus 1. So since I made the bases the same, then I can solve the equation by just saying this exponent needs to be equal to that one. And then solving it for x. So here I will add the 1 to both sides. So 6x equals 5. And divide both sides by 6. So x equals 5, 6. All right, number 5. 2 to the x equals 6. So can you rewrite 6 with a base of 2 using whole number exponents? No, it's going to be somewhere in between here, right? So what does that mean? What method am I going to have to use in order for that exponent to come down? I'm going to have to log both sides. So if I log the left, log of 2 to the x, I have to log the right. So log of 6. Now I can get my x out of the exponent using that property. So x times log 2 equals log 6. So now that your x is down here in the regular row, not up in the exponent anymore, I just need to isolate it. So I'm going to need to divide both sides by that log 2 to get the x by itself. So let's see, I've got log 6 divided by log 2, which I'll do in my calculator just like the last one. So log, or 2 ago. 6, close it, divided by log 2. And close it. There's your answer. Round it to 4 decimal places. So let's see what I've got. I've got 2.58496. Okay, so here's my 4th decimal place. So I need to see whether or not I need to round it up. Since this number is 5 or above, then I do need to round this up. Well, that's going to round both of those numbers up, right? So 2.5 that's a 9, it's going to round that up to 50. Right? Number 6. All right. I'm going to have to use the log method on this one because I can't rewrite 10 to have a base of 2 using whole number exponents. Okay, so I am going to log both sides to get these x's down out of the exponents. So I'm going to have log of 10 to the negative x equals log of 2 to the 6x. So now I can bring my exponents down. So now I have negative x log 10 equals 6x log 2. Now, something we haven't seen. I have what the whole point is to figure out what the x is. Okay? I have x's in 2 separate terms, even on 2 separate sides of the equation. Okay? If that's the case, you want to put these x's on the same side as each other. So let's see if I need to move this term over here. So I'm going to add x log 10 to both sides, and you'll see why in just a minute. So let's see, on this side I have a 0 equals, these are not like terms. They both have x's in them, but they're not like terms. They're different logs. So I'm just going to write these out all the way. So you have 6x log 2 plus x log 10. So the reason you put these on the same side together is that now they have an x in common. So you can actually, anytime 2 terms have something in common, you can pull that thing that's in common out and then put in parentheses what's left. So if I pull the x out of each of these terms, this one will just have 6 log 2 plus this one will just be log 10. So now you just have this x. So I want to divide by this to get this x by itself. So 6 log 2 plus log 10, both sides. But I don't even have to put this in my calculator because there's my x all by itself. Look at the left side. 0 is the numerator. If you have 0 in your numerator, it's not going to matter what's in your denominator because 0 over anything is 0. Right? Number 7. Right? E to the t power equals 629. And I'm solving for that t that's in the exponent. Okay. Now, instead of logging, just plain logging both sides, since this is an e, remember that log base e is equal to the natural log. Y'all can't see it. So if you're dealing with E, and you're trying to get that exponent down out of the exponent, instead of just plain logging both sides, ln both sides. You'll see why. In just a second. So it has the same property. So now my t can come down. So I'm going to have t times ln of E equals ln of 629. Now, remember that ln is log base E. So if I have log base E of E, remember, what is all this? If the base and what you're taking the log of are the same thing, that is equal to 1. So anytime you have ln of E, that is actually just a 1. So I have t times 1, which is just t, equals ln of 629. And then you just type that in your calculator. You've got the ln button right below the log button. So ln 629. Oops, leave it on. And then round it to 4 decimal places. Okay, so if I go 4 places behind the decimal, one more, it's a 3, which means I don't need to round up the 1. So 6.4441. Right, number 8. Another one with an E. E to the negative 0.15t equals 0.43. All right, so again, since I'm dealing with E, I'm going to ln both sides to get the exponent down. So ln of E to the negative 0.15t. Since I ln that side, I have to ln the other side. Now that brings my exponent down. So now in front of my ln E, I have negative 0.15t times ln of E equals ln of 0.43. But again, remember, this ln of E is just 1. So on the left, all I actually have left is that negative 0.15t equals ln of 0.43. So to get t by itself, I just need to divide by what's hooked onto it. So I'm dividing by negative 0.15. So now I have t equals, and then I'll just punch the right side in my calculator. So ln 0.43, close, and then divide it by negative 0.15. And then round it to 4 decimal places. So let's see, 1, 2, 3, 4. After that 4 is a 6, which means I'll round that 4 up to a 5. So I've got 5.6265. Right, number 9. Right, this is the last one of the exponential equations. That's a big one. Okay, number 9. You got 15 to the x equals 5 to the x plus 2. Okay, unfortunately, I can't rewrite this 15 with a base of 5. So I am going to log both sides. So let's see, log of 15 to the x is equal to log of 5 to the x plus 2. Okay, why do we do the logs? So we can bring the x's out of the exponents. So on the left, I've got x times log of 15 equals, now this one's different because it's got 2 terms in its exponent. So when you bring this exponent down and it's times log of 5, you actually are doing both of these times log of 5. So let's write that out. So x times log of 5 is x log of 5 plus 2 times log 5. So 2 log 5. Over here, I've got x of log 15. Now, remember what we did on the one when we were solving for x, but it was in 2 separate terms, and those terms weren't on the same side. We want to put these on the same side as each other so that I can pull out the x. So let's see, let's move this one to the left. So I'm doing minus x log 5 on both sides. So it cancels in here. So all I have left on the right is 2 log 5. On the left, I can't put these terms together, so I'm just going to have it all the way written out. X log 15 minus x log 5. So again, why did we put these on the same side? So that both terms that had the x will be together, and I can pull out that x, put in parentheses what's left after I take the x out of both of those. So this one would just be log 15 minus log 5. Still over here, 2 log 5. So to get this x by itself, I just need to divide by this. So I'm dividing by log of 15 minus log of 5 on both sides. So these cancel. So there's my x by itself. So if I could just simplify that other side, I'll have my answer, right? Because the x is by itself over here. Now, be careful when you type this in your calculator, because remember, once you hit that log key, it's automatically going to give you an open parenthesis that you'll have to close. Now, in the denominator, because it's got 2 terms, and I want to tell the calculator that both those terms are in the denominator, I have to do an open parenthesis here. Now, remember, it's going to give me an open parenthesis that I'll have to close after that log. Same here. But this parenthesis also needs to be closed, which means you're actually at the very end going to have 2 closing parentheses when you type it in. Okay, so let's look at how we would put it in the calculator, just like that. So up top, 2 log, so there's your open parenthesis, so log 5. Then close it, over or divided by. Here's where you're going to want to put an opening parenthesis to tell the calculator that everything I'm about to type is in this denominator of this fraction. So log 15. So log 15, then close that parenthesis, minus log 5. So minus log 5, and then here's where you got to close this parenthesis around the 5, and then you also got to close the parenthesis for the denominator. So you're just hitting it twice and then hit enter, and then rounding it to 4 spots. So let's see, 1, 2, 3, 4. After that, 9 is a 4, so I don't need to round it up. So 2.9299. Right, number 10. So that's how you do the exponential equations when the exponent is where your x is. Okay, so now we're going to do some log equations. So you have log base 6 of x equals 2. If you're solving a logarithmic equation and there's just one log in it, you're actually going to turn it into an exponential equation. Okay, and we did this in that section, maybe 9.2 or 9.3, when we first started talking about how you go back and forth between logs and exponents. Remember, this is the base of your logarithm. What's also going to be the base of your exponent, right? You're going to have 6 to that power. So 6 to the second power is going to be equal to what you're taking the log of, or what's in this position, which is x. So now you've already got your x isolated. Its x is by itself. I just need to know what 6 squared is, and it's 36. Okay, so again, if you just have one logarithmic expression in your equation, turn it into an exponential equation. All right, number 11. Log of x equals -1. So there is only one log. So I am going to turn it into an exponential equation, but I don't see the base of the log, which means that base is automatically 10, right? When you don't see the base, it's automatically 10. So I'm going to have 10 to the -1 power is equal to x. Okay, now 10, that you just type this in your calculator, right? The x is already isolated, so I just need to know what 10 to the -1 is. So when you type that in, you get 0.1. Right, number 12. Log base 5 of 4x minus 4 equals 4. Same thing, same method. One logarithm, so I'm going to do 5 to the 4th power. It's going to be equal to what's in this position, which is 4x minus 4. 5 to the 4th power gives me 625 equals 4x minus 4. Then just get your x by itself. So get rid of the -4 with a +4. So here I've got 4x equals 629, and then divide by 4. Okay, so you have x equals, it should take 629 over 4 since that fraction doesn't reduce. Okay, if not, you just type it in and then just give it that answer. It should take either one of these though. So 157.25. So either one of these should be fine answers. Number 13. All right. So something new. So the last problems just had one logarithm. So we just automatically turned it into an exponential equation. If you have two logs on the same side, your first thing you're going to want to do is we're going to use those simplifying rules that we just did in 9.5, where I can rewrite this as a single logarithm. What do the pluses turn into? If you're adding two logarithms, you can rewrite that as one logarithm and then multiply what you're taking the logs of. So x times x plus 48 equals 2. So now that I've rewritten the sum of those two logarithms as a single logarithm, now I can use the method that I've been doing because I only have one log, which means I need to say, okay, its base is 10. 10 to the second power equals what's in this position, that whole thing, x times x plus 48. Well, now let's see what we have. 10 squared is 100 equals, here if I distribute, x times x gives me x squared plus x times 48 is 48x. So now your x is not just an x. Your highest exponent is x to the second power, which means now this is a quad, right? X squared equations are quadratic equations where I need all the terms on one side. So I'm going to subtract this 100. So I've got 0 equals x squared plus 48x minus 100. You can take this to the quad program. Program down to quad. And then type in your A, B, and C, which will be 1, 48, and negative 100, which gives me negative 50 and 2. Okay. Also, if you don't have the quad program, you would have had to factor this. X and x for x squared, numbers that multiply to give me negative 100 and add to give me positive 48 are a positive 50 and negative 2. But when you set those equal to 0 and solve them for x, that's what changes their signs, right? If I solve this one for x, I have to subtract 50 from both sides, which would give me x equals negative 50. Here I would have to add 2 to both sides to get x equals 2. If you've got the quad program, that gave you those. But only one of those answers is a good answer because think about what you're solving for. Let's just look at this x. This negative 50. What happens if you try to do log negative 50? It's not a real answer, not a real number answer, right? Because you can't have a negative number right here. So the negative 50 is not a good answer. The answer is just that 2. Right, number 14. Log base 4 of c plus 16 minus log base 4 of c plus 7 equals log base 4 of c. So looking at the left side, since I have two log base 4s and they are subtracted, I'm going to simplify that. What does subtraction turn into? If you turn it into one logarithm, it's going to be a division or a fraction or a quotient problem. So I've got log base 4 of c plus 16 over c plus 7 equals, all I have over there is the log base 4 of c. So something new that we haven't seen is I do have two logs on separate sides. They're the same log though. So why can't I can do anything to one side as long as I do it to the other. So I'm just going to divide the logs off. Divide that side by log base 4, divide this side by log base 4. So that cancels it out. So all I'm left with is c plus 16 over c plus 7 equals c. So I'm trying to get c by itself, and I got c's everywhere, numerators, denominators by itself. If you are left with what's called a proportion, you can solve proportions by what's called cross multiplication, okay? A proportion means you have a fraction equal to, and I can make that side a fraction also. So the diagonal multiplication of this is going to be equal to multiplying diagonally the other way. Okay, so let's go this way first. So c times c plus 7. So both of these I'm multiplying times c, which is going to give me c squared plus 7c is equal to, multiply the other diagonal. Well, c plus 16 times 1 is just c plus 16. Now, once again, it's quad. So since it's quad, I'm going to bring these terms over here. So minus c minus 16. So here I've got 0 equals c squared plus, I put these c's together, so plus 6c minus 16. You can take that to quad. So if I take that to quad, if not, you'll have to factor it and type in A is 1, B is 6, C is negative 16. It gives me negative 8 and 2. But again, the negative 8, if you put it right here, it'll turn what's in that parentheses into negative 1. And you can't take the log of a negative number like that. So that negative 8 is not a good answer, just the positive 2. All right, let's look at number 15. 3 more, we can power through. Log base 3 of x plus 1 minus log base 3 of x equals 3. So let's see, I'm going to rewrite, since that's minus, I'm going to rewrite that as a division to simplify it into one logarithm. So log base 3 of x plus 1 over x equals 3. Now, at this point on the last one, I still have logs on both sides, so I just divided them off of both sides. I can't do that on this one because there's no log over here to divide off. This is back to, I've only got one logarithm. So I'm going to turn this into an exponential equation. 3 times, or excuse me, 3 to the third power is going to be equal to what's in this position, which is x plus 1 over x. So over here, 3 to the third power is 27 equals x plus 1 over x. I'm solving for x. It's all over the place. It is a proportion though. So let's use cross multiplying. Doesn't matter which way you go first. 27 times x is 27x equals 1 times x plus 1. Well, 1 times anything doesn't change anything, so it's just x plus 1. So this one doesn't have an x squared. It's just plain x, right? There's no quad involved because there's not an x squared. So I'm just going to get the x by, just move this x over here. So now I've got 26x equals 1, and then divide it by 26. So what does x equal? Just that 1 over 26. All right, 2 more. Number 16. ln of x plus ln of x minus 1 equals ln of 2. Okay, so let's see. Since I'm going to rewrite this, since it's the sum, in order for it to be one logarithm, it's going to be the x times the x minus 1. So ln of x times x minus 1 equals ln of 2. So what do you do when you have logs on both sides? Just divide them off now to cancel both logs. So now I'm left with x times x minus 1. So I'll distribute x squared minus 1x equals 2. So once again, it's squared, which means it's quad. So I'm going to bring this 2 over. I'm going to subtract 2 from both sides. So now I've got x squared minus 1x minus 2 equals 0. So you can definitely go to quad. If you don't have quad, you'll have to factor this. X and x for x squared. Numbers that multiply to give me negative 2 and add to give me negative 1 are a negative 2 and positive 1. But when I set these equal to 0, this will end up being x equals positive 2. That'll end up being x equals negative 1. Since that's an ln of x, I can't have that negative answer. So again, 2 is the only true answer. Last one, got 1 minute. Log base 3 of x plus 4. Plus log base 3 of x minus 4. Equals 2. All right, so that left side, I'm going to simplify it by turning it into a single logarithm. Since it's adding, I'm going to turn it into a single log base 3 and multiply these. So x plus 4, x minus 4 equals 2. So I only have a single logarithm. When you just have the single logarithm, you turn it into exponential. So 3 squared equals, what's in this position is all this, x plus 4, x minus 4. So now let's see, 3 squared is 9. When I multiply this together, x times x gives me x squared. X times negative 4 is negative 4x. My inner and last are positive 4 times x. And my last positive 4 times negative 4 is negative 16. What happens to these x's? They cancel each other out. So all I have on the right is x squared minus 16. It's quad again. So this 9, I'm going to have to subtract off both sides. So 0 equals x squared minus 25. You can put that in quad, or it's just a difference of power. I can factor this. If you factor, it's x and x for the x squared. And then what's the same number that you multiply together and get 25? 5 and 5, one's a plus and one's a minus. But if you set this equal to 0 and solve it for x, you would have to subtract the 5 from both sides, and that would give you -5. This one, you set that equal to 0 and solve it, you'd have to add the 5 to both sides, so you would get x equals +5. I can't do -5 because it's going to turn what I'm taking the logarithm of into a negative number. So the only answer is that +5. Whew, that is a lot.